features of graphs of functions. And to do that, I want to have some kind of visual reference here. Oh, come on now. It didn't work. So here's the, oops. Here's the x-axis, here's the y-axis, and we'll take each one of my little grid squares to be 1 unit here for our measurement, 1 and 1, 0. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, and that's our scale. So the first thing that I want to talk about is intervals of increase, decrease, and constant. So what does that mean? So first of all, when we talk about numbers on the x-axis and when we write intervals, we always describe things from smallest to largest. Smallest to largest, or this is red, left to right. So when we describe this, it's almost as if we're talking about motion from left to right, or this is some crazy roller coaster, and we're moving along the roller coaster from left to right. Now, that's a good way to help us organize our thoughts on this, because when we talk about increase or decrease or constant, what we're talking about is, as we move from left to right along the curve, is the curve rising, is the curve falling, or is the curve staying constant? And then we describe that in terms of intervals of x. So let's get some formal definitions here. A function is increasing on an interval a to b, open interval a to b, if for any two values, x1 and x2 in the interval a to b, we have f of x1 is less than f of x2 whenever x1 is less than x2. Now that's a super mathematically complicated way of saying the following. So let's talk about that. So here's an interval. Let's see, we'll put A on here and we'll put B on here. And what's going on is we're choosing any two random x values in between A and B. Maybe this one and that one. And this says here, whenever x1 is less than x2, so that means x1 is on the left and x2 is on the right, x1 is less than x2, then whatever the y values are that go with it, maybe that's f of x1, and f of x2 needs to be larger than it, f of x2. That is to say, this property has to hold. For any 2 points that you choose where x1 is on the left of x2, then f of x2 has to be higher than f of x1. And if that's the case, then what you're going to get is the curve that is rising over that interval. Now, in our particular case, if we look at this, I highlight this in red, as we move from left to right, the curve is rising, it's rising, it's rising until it gets to this point. And then it starts dropping. And it doesn't start actually rising again until I get here, and then it's rising again here. And so for our open intervals, we would say that f of x is increasing over the interval. Here we go. So first of all, I guess I should say this. We need a better highlighter color. We're always talking about increase and decrease on an open interval. So I'm actually ignoring this closed dot right here. So where is that? That's at -2. And then at +2, it stops increasing. So it's increasing from -2 to +2. These are the x values. And then it starts up again at 5, 6, 7, 8, 9. And then it's increasing from 7 to 9. And then 11, 12, 13. And then again from 11 to 13, not including the endpoints. And then we would join those intervals together with a union. And that would be my interval or intervals of increase for this function. So this is always relative to x values. Now I'm going to say this again, and I said it before a couple of days ago, or maybe Monday. Do not confuse open intervals with ordered pairs. These are not ordered pairs. These are intervals, not ordered pairs. So be careful about how you interpret that. You got to make sure you get that information straight in your head. Is that okay? Does anybody have any questions on that? Okie doke. You guys were doing so good with interacting with me, and now we're kind of falling off. It's hard. The third day is rough. You guys make it through this week. Random question, but I saw the union sign upside down in the homework. What does that mean? That's intersection. We actually talked about that yesterday briefly. We did some examples, and so you'll find some intersection examples on, oh, I forget which video it is. Let me see here. When do we do that? We do that in the arithmetic of functions. I think it's lecture 1.5.2, the domain of arithmetic functions, where we have to combine domains and we talk about intersection. So I talked about it a little bit later than I should have, but if you look at video 1.5.2, Savvy, you should have a better idea of what that's about. So it's called the intersection. Yeah. No, I know a lot of people miss videos because I've been busting my butt to get these videos up online, and I have like maybe one view. So, you know, thanks. Okay, anyway, yeah, take a look at that. Okay, so that is increasing. Similarly, a function f of x is decreasing from left to right on an interval a to b if for x1 and x2 in AB, whenever x1 is less than x2, f of x1 is greater than f of x2. So let's talk about that. Again, we have a number line here. Maybe here's A, here's B, and somewhere in between is an x1, again, that's less than an x2. x1 less than x2. But this time, whatever the ordered pair is that has a height of f of x1, that one is greater than f of x2. And if that's true for every x1 and x2 in the interval, then this is going to be decreasing. So if we come back up here and duplicate this lovely diagram, and I choose a different color, as we move from left to right, after this top point here, it starts to decrease. We start going down the slide. And it looks like that's my only interval of decrease here. And so f of x, I'll write that over here. Here, f of x is decreasing over the interval, the open interval, I should say. So let's see, that's from 2 up to 7, from 2 to 7. Or, if you like, 2 is less than x is less than 7 in interval notation. But, or sorry, inequality notation. But we're really looking for this interval notation. That's how we want to express this. And then finally, f of x is constant on an interval a to b if f of x1 equals f of x2 for all x1 and x2 in that interval a to b. So again, what that means for us is if we have some interval between a and b, and we choose an x1 and an x2 in that interval at random, f of x1 will have the same height as f of x2. And if that happens everywhere in that interval, then we have a what's called a constant interval. That is to say, the function is not rising or falling from left to right. And for us, it's going to be this interval right here. So f of x is constant over the interval 9 to 11. And that's the idea. And so the book is going to give you a bunch of pictures of graphs, and you're just supposed to be able to look right at it and say it's increasing on this interval, it's decreasing on that interval. And you may have to use a union symbol like we did in this first one to sort of, oops, where did it go? Right here. So let me color code these, I guess. Let's see. That was our increasing. Our decreasing was lavender man. Oh, I already did that one. And then our constant was seafoam green. What a lovely color that is. Easter pastels, man. Okay, so that's increasing, decreasing, and constant intervals. More features of this graph. The next thing that I want to talk about, again, while the definition is sort of wordy and cryptic, the concept is really straightforward. So I want to talk about maximums and minimums. Oops, minimums of a function. A function f of x has a maximum value at the point x comma, oh, let me use a different letter here. Let's say c comma f of c. So that means that the x value is some c value and the output y is whatever the function gives you when you plug in c. We'll have a maximum value at cf of c if for c in some interval a to b, we have f of c is greater than or equal to f of x for all x in the interval a to b. Okay, so what is that talking about? Let me just draw a little picture here. Okay, so here's the deal. This is my curve, f of x, right? Now, as cryptic as that definition might be, x, y, all we're really looking for here is the highest point in a given interval. In fact, you know what? Actually, let me change this a little bit. There, that's better. So it looks like, in this particular case, there are two relatively high points on this graph. They are the mountain peaks, and they are as follows. This point is the highest point in a small neighborhood, and there's some point up here. Maybe that guy. And so we might say here that both points, now these aren't intervals, these are points. Let's see, that's 1, 3. 1, 3, and 1, 2, 3, 4, 5, 6, 7. 3, 4, 5, 6. This is 7, 6, and this is 1, 3. And 7, 6 are what are called relative maximums of the function. Now, while it is true that this particular point is the highest point on the curve, when we say relative, we mean in a small neighborhood. And so of all the points close to this point, this is the highest one in its neighborhood. These are the people in my neighborhood, man. And of all the points near this point, and all the points on the curve around this point, that point is largest. So these are our maximums. So you're basically supposed to look at a graph and say, these are the high points, and then say these are the maximums and give a location. Similarly, a function, f of x, has a, let's say, a relative minimum. Excuse me, relative minimum at any point c f of c, such that f of c is less than or equal to f of x for all x in a small interval containing c. So here what we have, and I'll just use the same picture. This is very telling. Oops. Shrink. No, I don't want to shrink it. There, something like that. Okay, so what are the low points here? Well, you got to be careful. There's one over here somewhere. Let's put a point on there. That's a low point. That's our bottom. That's our valley. That's our lowest spot. And so it would appear here that we have a relative minimum at what looks like 2.52. And so we have a relative minimum at 2.5, 2. Now, Are there any other low spots on this graph? And you got to be careful here.
No, because there's an open circle.
Yes, this is not a minimum. There is no point there. So we want to note, what would that be? That would have been like something like 8, 2.5. Note 8, 2.5 is not a minimum, as there is no point at the open dot. So watch out for that kind of thing. It's actually missing it. So, and you might say, well, what about the point right before it? What about that point? Well, if you actually were to zoom in here, zoom times a billion, right? It would come in here and look like this. But when you choose a specific point, there's always going to be more points in between there. You're never actually going to get closer. And if you want to say, well, I'll just choose a point that's closer, I'll choose that point. Well, then you can zoom in again. And you're going to find out that there's always more space in between. So you're never actually going to get to the lowest point there. If it's an open dot, you're going to be constantly missing the mark as you try to get ever closer there. It's one of those lovely ideas that'll drive you crazy. So watch out for that kind of thing. Now, in terms of our graph that we had up here, let's see. Oops. For our curve, f of x above, let's see. Let me erase some of this color here. Oh, step back, Jack. We have relative maxes at, let's see, that point there and that point there. Those are our two relative maxes. That is 2, 5, and that is 13, 6 at 2, 5 and 13, 6. Those are not intervals. These are ordered pairs. So watch out. It can be really confusing if you're not on top of intervals versus ordered pairs. Watch out for that kind of thing. And then we have relative minimums at, let's see. We got one there. And that's it. That's our only relative minimum. Relative minimum at, oops, this is a -2. -2, 3, -3, -2, -3. This is bugging me. I have to shift this. There, that's better. And then one other thing that we're supposed to talk about are x and y intercepts, right? And we've already talked about that before, but finally, x and y intercepts are points on the graph which are on the x or y axis respectively. So for us in this particular case, we hit an axis. We hit an axis there. We hit an axis there, there, and there. And so those are our x and y intercepts. And so we have x intercepts at -1, 0, 4, 0, and 8, 0. And we have y-intercepts at, what was that, 0, 3, 0, 3. So those are just some features. And look, most of this in this section is literally about looking at the graph and being able to just write down what you see in notation. Can you talk about intervals of increase, decrease, and constant? Can you call out the maximums and minimums? Do you know how to deal with weird stuff like open dots? And then, of course, the x and y intercepts. And that is the majority of 1.6. There's one more idea I'd like to talk about in 1.6. But before we go on, is anybody unclear about anything that we just talked about? Does anybody have any questions?